In physics, the Eightfold Way is a term coined by American physicist Murray Gell-Mann for a theory organizing subatomic baryons and mesons into octets. The theory was independently proposed by Israeli physicist Yuval Ne'eman and led to the subsequent development of the quark model. In addition to organizing the mesons and spin 1/2 baryons into an octet, the principles of the Eightfold Way also applied to the spin 3/2 baryons, forming a decouplet. However, one of the particles of this decouplet had never been previously observed. Gell-Mann called this particle the omega- and predicted in 1962 that it would have a strangeness -3, electric charge -1 and a mass near 7003168000000000000001680 MeV, C2. In 1964, a particle closely matching these predictions was discovered by a particle accelerator group at Brookhaven. Gell-Mann received the 1969 Nobel Prize in Physics for his work on the theory of elementary particles. The Eightfold Way may be understood in modern terms as a consequence of flavor symmetries between various kinds of quarks. Since the strong nuclear force affects quarks the same way regardless of their flavor, replacing one flavor of quark with another in a hadron should not alter its mass very much. Mathematically, this replacement may be described by elements of the SU group. The octets and other arrangements are representations of this group. Background: flavor symmetry. There is an abstract three-dimensional vector space, and the laws of physics are approximately invariant under applying a determinant 1 unitary transformation to this space. Here, SU refers to the Lie group of 3 times 3 unitary matrices with determinant 1. For example, the flavor rotation is a transformation that simultaneously turns all the up quarks in the universe into down quarks and vice versa. More specifically, these flavor rotations are exact symmetries if you only look at strong force interactions. But they are not truly exact symmetries of the universe because the 3 quarks have different masses and different electroweak interactions. This approximate symmetry is called flavor symmetry, or more specifically flavor SU symmetry. Connection to representation theory. Assume we have a certain particle, for example, a proton, in a quantum state. If we apply one of the flavor rotations A to our particle, it enters a new quantum state which we can call, depending on A, this new state might be a proton, or a neutron, or a superposition of a proton and a neutron, or various other possibilities. The set of all possible quantum states spans a vector space. Representation theory is a mathematical theory that describes the situation where elements of a group are automorphisms of a vector space. Therefore, by studying the representation theory of SU, we can learn the possibilities for what the vector space is and how it is affected by flavor symmetry. Since the flavor rotations A are approximate, not exact, symmetries, each orthogonal state in the vector space corresponds to a different particle species. In the example above, when a proton is transformed by every possible flavor rotation A, it turns out that it moves around in 8-dimensional vector space. Those 8 dimensions correspond to the 8 particles in the so-called baryon octet. This corresponds to an 8-dimensional representation of the group SU. Since A is an approximate symmetry, all the particles in this octet have similar mass. Incidentally, every Lie group has a corresponding Lie algebra, and each group representation of the Lie group can be mapped to a corresponding Lie algebra representation on the same vector space. The Lie algebra SU can be written as the set of 3 times 3 traceless Hermitian matrices. Physicists generally discuss the representation theory of the Lie algebra SU instead of the Lie group SU, since the former is simpler and the two are ultimately equivalent. Development in the text above. Flavor symmetry was defined and motivated using our modern understanding of quarks, but historically, it was the reverse. Quarks were motivated by our understanding of flavor symmetry. Specifically, First, it was noticed that groups of particles were related to each other in a way that matched the representation theory of SU. From that, it was inferred that there is an approximate symmetry of the universe which is parametrized by the group SU. Finally, this helped lead to the discovery of quarks, 3 of which are interchanged by these SU transformations.